Always a good idea to ask me.
We did.
Sometimes I forget. Thank you. All right, so replace E with L. All right, this is for acyclic aldehyde. So basically just straight chains without a ring. Whenever you number your carbons, you want to number it so your carbonyl carbon, your aldehyde carbon specifically, is number 1. So it's going to take priority over anything else that we've talked about so far, no matter what. And this is in both rings and, or both cyclic and acyclic. In rings, it's going to be number 1, but you actually don't have to label it as number 1 because it's assumed. Actually, you actually don't have to call it number 1 for either one of them. Now that I think about it, acyclic or cyclic, because by definition, if you have an aldehyde, this carbon is number 1. So you don't have to say 1 hexanal. You can just say hexanal. All right. Now, for cyclic aldehydes, you don't use the al suffix. For cyclic aldehyde, you name as an alkane. Right, so cyclopentane, cyclohexane, whatever. And then you add the suffix carbaldehyde. To the end. So if you had a cyclic 6-carbon aldehyde, it would be cyclohexane carbaldehyde. You may wonder, why do they not follow the rules for acyclic? Why not, instead of cyclohexane carbaldehyde, why don't they just call it cyclohexanol? I have no idea. If you have some questions or concerns, you can write the International Union of Pure Biochemistry. They makes the rules, so we follow them. But yeah, I always agreed. I thought that kind of sounded stupid, but that's what they do. Okay. So take a look at a couple of them here. A little practice. All right, let's name this one. Whenever you get something, let me know what the parent name should be. What's the longest carbon chain with your aldehyde group? How many carbons? What's that? Octane? 8 carbons? I would agree with that. Right there. Okay. So if it's an aldehyde, it's not going to be octane, though. It's going to be octanol. Octanol. And again, we don't have to say 1 octanol because we assume the aldehyde carbon is number 1. All right, so this is number one. We have 2, 3, 4, 5, 6, 7, 8. So all we have to do is just finish the substituents now. What do we have substituent wise? We have 2, 5, 6 trimethyl. Yep. 2, 5, 6 trimethyl octanol. Okay. Any questions so far? Pretty simple. Let's see. I'm just making this up off the top of my head, so let's see. All right, let's think of something else. Let's think of chlorine in there. Make it interesting. All right, this one's got a few more features in it, but the approach is basically the same, right? Bless you. First question is going to be, what is our parent chain? What's that? Pentanal. Let's see. Hexanal. Yeah. Yes, it is hexanal. Important distinction. Hexanol is an alcohol, so be sure to use the short A sound for aldehydes. Yeah, this one's going to be hexanal. Longest carbon chain with your aldehyde. 6 carbons. Right. By definition, carbon in the aldehyde is number 1, 2, 3, 4, 5, 6. You notice you have an OH group in there, and we've seen in the past that's pretty important. But it's not important enough to take priority over the aldehyde. So in this case, we don't name this as an alcohol. We name it as an aldehyde. We treat this as a substituent. What do you call an OH as a substituent group? Hydroxy. Yep. So we have a chlorine at number 2, a hydroxy at 3, and 2 methyls at 5. So going in alphabetical order, that's going to be 2 chloro, 3 hydroxy. I'm running out of room. And we have 2 methyl groups at number 5. 5, 5, dimethyl hexanal. Yep. Does that make sense? Any questions so far? All right. Let's try that one. All right, when somebody has a suggestion for the parent name, let me know. What's the parent name here? Shy this one. All right. What's the rules for cyclic aldehydes? How do we find the parent name? All right, so what you do, you name the ring first as an alkane. And Josh, you said this is cyclobutane, and it is. All right. Now, that in no way identifies this as an aldehyde, though. How do we identify it as an aldehyde? Add carbaldehyde to the end. It's actually all one word. You can believe that. Cyclohexane carbaldehyde, all one word. Yeah. The biggest mistake people make is tripping up and going into naming this as cyclobutanol, which is very understandable, but it's not the rules, right? As always, this one's going to be carbon number 1. We don't have to say 1 cyclobutane carbaldehyde, though, right? It doesn't matter in this case which direction we number, but we're going to get the same thing anyway. So substituent-wise, we're going to have 3,3 dichloro. 3,3 dichlorocyclobutane carbaldehyde. Okay. Are there any questions about how we got that? Does that make sense? Okay. That's basically it as far as the IUPAC naming of aldehydes. They're pretty simple. There isn't really much of a common name system that's used for aldehydes. However, there are 3 aldehydes that are very well known by common names. I just want to highlight those. You guys should know what this is. You've probably worked with it before. What's that? That is formaldehyde. Formaldehyde is actually a common name. It's not a systematic name. The systematic name for this is methanol, but probably better known as formaldehyde. So that's what people are talking about when they say formaldehyde. Adding 1 carbon gives you this, which is commonly known as acetaldehyde. And then another one that's very well known by its common name is this, an aldehyde attached to a benzene ring. That's commonly known as benzaldehyde. Benzaldehyde's that awesome aldehyde I mentioned the other day. It smells like cherries. Yeah, it smells like maraschino cherries. There's not benzaldehyde in maraschino cherries, though. That would be bad. There's other things that smell like that, too. That's an ester of some sort that gives it this smell. All right. All right. So that's basically all there is for the aldehyde nomenclature. Let's talk about ketones. Ketones are nice because they don't have separate rules for cyclic or acyclic. You don't have this weird carbaldehyde like rule thing in there. You just treat them the same, right? To find the longest chain or ring, depending on what you might have, with carbonyl group. Number to give that carbonyl. The lowest possible number. In a ketone, there's one number that will never, ever be assigned to the carbonyl carbon. Any guesses? Don't say 0, that doesn't count. 1. Why 1?
Because we make it an alcohol.
Yeah, by definition, a ketone has the carbon in the middle of the chain. If it was on the end, it'd be an aldehyde, right? So this will never be carbon number 1, but you do want to number the chain or ring to give it the lowest possible number. I take that back. There is one situation where this can be carbon number 1, and that's when it's in a ring. I'll show you that in a second, but not in a straight chain. We're going to name as an alkane, but you're going to change the E to -one, not 1. It's not butan 1, it's butanone. Okay. Let's try a couple of these. All right, let's see. That'll work. Let's try that one. All right. First, we're going to find the parent chain, as always. What would the parent chain be here? You're trying to make me look foolish here, uncomfortable, staring at you. Please don't do that. Makes me sad. Thank you. What's that? It's hard to say, isn't it? Yeah. The longest carbon chain is this. It's 9 carbons that contains the carbonyl, right? That's nonane. And then you change that to -one, to a ketone. It's nonanone or nonanone. It's kind of a tongue twister. But that's what it is, nonanone. Now, you do have to tell where the carbonyl is located, or else, because this carbonyl could have been here, 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 here. It could have been lots of different places, right? So what number is the carbonyl carbon? What's that? 3. Yeah. You number the chain to give this the lowest possible number, even though it's not number 1. So this is 3 nonanone. And then all we have to do is take care of the substituents, right? We have a bromo at 5. We have an isopropyl at 6. So this is 5 bromo, 6 isopropyl. 3 none of them. Okay. Any questions on that one? All right, let's try this one. All right, this is a cyclic ketone. And you see in cyclic ketones, the carbonyl is built right into the ring. So what would the parent chain for this one be? Close, not hexanone. Cyclohexanone, yeah. We name it as an alkane, so that's cyclohexane. But we drop the E, add an O-N-E, that is cyclohexanone. All right. We're going to start numbering up here. So in this case, and when it's part of a ring, the carbon, the ketone carbon is actually number 1. Although you don't have to specify it in the name, because by definition, wherever this is in the ring is number 1. So we can just leave it like that. We're going to go clockwise because that gives substituents the lowest possible number. So we have an we have a tert-butyl group at number 3, a methyl at number 4. So 3 tert-butyl, 4 methyl cyclohexanol. Okay. Are there any questions about how we got that name? Does that make sense? Excellent. All right. Now, unlike aldehydes, there actually is a common name system. Ketones, for simple ones. Now, if you got a whole bunch of like substituents and stuff like that hanging off, you don't really want to do this. But if you have a simple ketone, you can use this system. Number 1. Name each R group that's attached to your carbonyl carbon. Remember, in ketones, you have a carbonyl carbon and you have 2 R groups attached. All right, so name each R group and alphabetize. If they're identical, you just use the prefix di. But otherwise, if they're different, you alphabetize them. And then you just simply add the word ketone to the end. So like that one, for instance, the IUPAC name for that one is 2-butanone, but it's commonly known as ethyl methyl ketone. Because there's an ethyl group right here and a methyl group right there on the other side of the carbonyl carbon. What would the common name of that one be? Diisopropyl ketone, very good. Yeah. Now again, the longer the chains get and the more stuff you have hanging off of them, it gets really, really difficult to do it this way. So when you get to more complex ketones, systematics, or the IUPAC, excuse me, is the best way to go. That being said, there's also 3 other ones that are commonly known by non-systematic common names. Sort of like with the aldehydes. You guys should know what that is. You use it all the time. What is it? Who said that? Acetone? Yeah. This is acetone. It's actually 2-propanone, but much more commonly known as acetone. So that's a name that you'll hear quite a bit. This one is one you'll hear quite a bit. This is acetophenone. And that one is known as benzophenone. Again, these common names don't necessarily abide by a common name system. They just kind of have been ascribed over the years. So good to kind of, remember some of those so that you recognize them. All right. Any questions about nomenclature of aldehydes or ketones? That's basically about it. It's pretty simple. All right, let's move on. Let's get into the good stuff now. Reactions. Ooh, reactions. I heard a derisive noise. I don't know who did it. Give you a freebie because this is fun. All right. Now, one thing that you're going to notice a lot in this chapter is it's kind of a long chapter, but a long chapter in the book, but a lot of that is actually kind of review because we've actually gone over some of this stuff already. For example, in the last chapter, we talked about hydride reductions in organometallics and how they react after with aldehydes and ketones. They actually do a kind of a nice job summarizing some of the reactions in here. So if you're looking for like a short form summary, like table type thing, they should have something like that in this chapter for aldehydes and ketones. It's kind of nice. But we're gonna skip all that since we've done it before. We're gonna get into the new stuff. It's new stuff, but again, it's gonna be kind of familiar, right? Because let's just say you have an aldehyde or a ketone. I'll just put acetone, right? What's one thing that's been consistent about reactions of aldehydes and ketones? Where are they reactive? Where's the reactive spot? What keeps getting attacked? Carbonyl carbon, yeah. We said previously that this carbonyl carbon has such a strong partial positive, it makes it a really good target of nucleophiles. And that's basically what we're doing in this chapter here. Just like we did with hydride reductions and organometallics, we're just using different nucleophiles. All right? So, first thing I want to talk about is synthesis of something called cyanohydrins. What is a cyanohydrin? I'll tell you in just a second after we make it. All right, so again, I'll just use acetone as an example. All right, you can take an aldehyde or a ketone, and you can react it with sodium cyanide, followed up by an acidic medium. I'm just going to use hydronium ion. The book uses HCl. It turns out it's the same. All right. Let's take a look at this. Sodium cyanide. What do you think sodium cyanide is going to give us? What's it going to serve as a source of? Well, what does sodium hydroxide serve as a source of? An OH minus group, right? So what do you think sodium cyanide serves as a source of? Cn minus, yeah. It's a salt, right? Sodium salt. It's going to dissociate, and we don't care about that anymore. Yeah, it gives you the cyanide group, Cn minus. That's a strong nucleophile. What do you think the strong nucleophile is going to do? Back to carbonyl carbon, boom, yeah. Same thing that we've been doing, just a different nucleophile. All right, do ketones undergo nucleophilic additions or substitutions? Not substitutions. There you go, it is additions, yeah. The reason there's no substitutions because there's no good leaving group, right? So, just like we did with the last chapter, the electrons are going to move up to oxygen. You have a negative O, and the acid is going to protonate it. Water is actually not strong enough in this case. We used water as a proton source last chapter. Here you need something with a little bit more kick to it. So that's why we actually use an acidic solution. And voila, you have your cyanohydrin. A cyanohydrin is defined as a compound that's got an OH and a CN attached to the same carbon. OH and a CN attached to the same carbon. Follows a very, very simple mechanism, simple attack on the carbonyl carbon, elevation of electrons, protonation, so nucleophilic addition. They're not quite all this directly simple. So this is kind of your introduction, kind of your first one, get your feet wet. Okay? But honestly, like I said, it's not any different than the ones you've been doing previously. You're just using a different nucleophile. Okay. Any questions on this one? Fun thing you can do with cyanohydrins too. We're going to introduce our first hydrolysis reaction. You guys heard the term hydrolysis before? You may have heard it in Gen Chem. Yay, nay, possibly. Do you know what it is? No, I didn't. Hydrolysis is a very wide definition. Basically, when you do a hydrolysis, you're basically using water in some form to sort of destroy bonds. And oftentimes you make new ones in its place. Very, very broad, vague definition because hydrolysis happens in a lot of different ways, right? But when you do a hydrolysis, that basically tells you that water is going to be one of your reagents. All right, let's say you have a cyanohydrin. Something like that. Basically what happens, and this is not a mechanism one, we don't have the mechanism for this one, this is something you're just going to remember. When you do a hydrolysis here, you're going to have H2O, and I think it is an acid, or OH, okay. You add water in either acidic or basic media, doesn't matter which one, and you add heat. And basically what happens here is that you will hydrolyze or destroy that CN group. And what happens to it? Yep. That carbon gets converted into a carboxylic acid. Again, this is kind of just one that you have to remember. We're going to see several other examples, though. Honestly, I'll be brutally honest, this reaction isn't that important, but it's good to include this because you're going to see several examples of hydrolysis over the next couple of chapters, right? So good to go ahead and introduce it and sort of show you the basic definition. Use water to kind of destroy bonds and make something else. Yeah. Any questions? All right. The next one is really cool. I like it. Super useful. This is called the Wittig reaction. Not Wittig, it's German, so it's Wittig. All right, when the Wittig reaction is basically a way to go from an aldehyde or ketone to an alkene. And to do this, you need something called Wittig reagent. What the heck is Wittig reagent? Wittig reagent is going to be similar to like Grignard reagent and organolithiums in that you make them. You kind of design them yourself to be used immediately for your purposes. All right. So the first thing I need to show you here is how you make a Wittig reagent. All right. It all starts with this. All right. When I write a big P little h like that, that stands for phenyl. And that just basically means a benzene ring hanging off of something else. Benzene ring as a substituent. All right, so this molecule, which is called triphenylphosphine, basically what it is, it's a phosphorus that's got 3 benzene rings hanging off of it. And you know, I don't really want to draw that over and over again. You probably don't either, so that's why we use the abbreviation, right? So that's always the first ingredient in making a Wittig reagent. You need triphenylphosphine. And what you're going to try to do is you're going to try to get an R group on there. And again, this R group can be methyl, ethyl, propyl, tert-butyl. It can be anything that you want. You just have to reuse the right alkyl halide. All right. For an example, I don't know, I'll just use one with a propyl group. All right. So I'm trying to get a propyl group on my Wittig reagent. What's going to happen is the phosphorus has a couple of extra electrons, and you're just simply going to get a nucleophilic substitution. It's going to attack that carbon. It's going to kick off your BR. And it's going to give you that. Phosphorus has got a positive charge. It was neutral. Now it's sharing electrons, so it acquires a positive charge. All right. Now we're not done yet, though, because what we want, in order for this to truly function as a Wittig reagent, this carbon, the one right next to your phosphorus, needs to be negative. We've got to get this one negative. That means we've got to pluck a hydrogen off of it. And if you remember, bases love to pluck hydrogens. We need a very specific base here. In fact, we are going to use a very specific organolithium, one called butyl lithium. That's going to be our base. Butyl lithium is going to grab a proton from that carbon. And it's going to leave you with that. That is your Wittig reagent. So it's kind of unusual looking, right? You have a positive charge and a negative charge right next to each other. I should tell you what that is. That actually is a general name for this type of structure. It's called an ylide. Spelled really weird too, Y-L-I-D-E. Some people call it a Y-lide. Those people are wrong, but yeah, whatever helps you remember. Yeah, ylide has two opposite charges right next to each other. Okay? Just so you know, this can be represented as a resonance structure. This pair of electrons can swoop down here and make a double bond with phosphorus. So you could see this represented that way as well. They basically mean the same thing. They're just two resonance forms. However, for mechanism purposes, this one's much easier to work with as far as like showing the reaction. So that's the one I'm going to be using. Okay. So that's how you make the Wittig reagent. And again, it's customizable. Use whatever alkyl halide you need in order to get whatever R group that you want. Okay? All right. Well, let's do something with this. Let's take, I don't know, we'll just do this aldehyde. See where we go with it, all right? So what you can then do is you can take your aldehyde or ketone and you can take your freshly made Wittig reagent. All right? Now, looking at this, we saw in a bunch of previous reactions, this is a good target, right? And it still is. Do you think anything's going to target this carbonyl carbon? If so, what is it? What's going to target that carbonyl carbon? The negative carbon, right? Good nucleophile, good target for nucleophile. So this is going to attack that. However, this one is a little bit different than some of the ones we've done because this does not detach itself from phosphorus yet. You also have a positive phosphorus. Simultaneously, this phosphorus is also going to attack your partial negative oxygen. Yeah, definitely kind of different. So what happens is you're going to end up making a funny little box structure. All right, so there's your O. A pair of pi electrons are used to make the bond between oxygen and phosphorus. You still have the benzene ring sort of out here. And then the phosphorus still has the 3 carbons. And remember, this carbon attacked this one. That's where that bond comes from. Definitely a very unique mechanism. Follows some of the same principles we've learned, but with little tweaks. Okay. Any questions? Y'all with me so far? All right. Now this doesn't last very long. It's not very stable. So what's going to happen is you're going to break 2 bonds. this bond's going to break and go up there. So you're going to end up making this as a byproduct. And also, this bond right here will break over there. And that is what makes your alkene. And I drew the trans here, but you do get a sort of a cis and trans mix. So it's not stereo specific. It is specific about where it puts the double bond, like between which two carbons. Okay. Does that make sense? Are there any questions about how we did that? Now, one thing that you can do with this, if you can remember this, these can be super easy to solve. If you're just doing a predict the product, really all that happens here is that you end up replacing this oxygen with this R group in the end, right? This carbon still has a double bond on it in your product, but it's just replaced by whatever R group, or the oxygen is just replaced by whatever R group. So if you see the setup, even if you don't know the mechanism, it's actually pretty easy to predict the product. Although, let's be real, I'm going to ask you to do the mechanism, so you should know it as well. All right, what's up? Crud. Things are just getting good. All right, we're about out of time. Any questions? All right, so as I so unfortunately realized last week, thanks, Sarah. No, I'm glad you told me, actually. Palmer is this week, which is a good thing. I like Palmer. Unfortunately, it does mean we can't meet for class on Wednesday, so I know you guys are probably pretty broken up about that. So we won't meet for class on Wednesday. Lab also doesn't meet because classes for the entire day are scheduled, are canceled. I don't know yet what I'm going to do about lab this week, so let me think on that. I'll get you something hopefully by the end of the day or tomorrow. But I'll let you know ahead of time. But that's all I got.